Welcome back. In this lecture, we will look at the characteristic of a semiconductor electrolyte interface when it is polarized, and because of polarization, the current features changes. Even though we mentioned that the important feature of a semiconductor is that it can absorb light, here our analysis will be based on a condition wherein the semiconductor is not absorbing light. So we'll first understand this case wherein there is current flow in the dark in the absence of light at the semiconductor electrolyte interface before we move on to understanding a current response when there is light. So we have covered all these things in previous two lectures. Uh, Mismatch of energy levels between semiconductor electrolyte gives rise to charge flow, gives rise to equilibration of electronic energy levels between semiconductor and the electrolyte, which in turn gives rise to band bending, which is critical for separating electron hole pair. What in this representation, we have made an approximation. That is, here it is completely depleted of free carriers, free electronic carriers, right? So this is an approximation that is true at 0 Kelvin. However, when there is finite temperature, we have to include Boltzmann statistics. What we mean by that? Again, we have done these kind of analysis in previous lectures, especially when we looked at Debye-Huckel theory, but we will try to understand what is this formula about. So supposing the concentration of free carriers is NB, NB refers to free carriers in the bulk, and the bulk is, let's say, at potential V, and Nx refers to the concentration of free carriers at a position X, wherein the potential is V of X. So this is the potential energy of the free carriers in a particular region, Vx, and this is the thermal energy available to the free carriers. So effectively, this is a kind of Maxwell-Boltzmann or Boltzmann distribution. So where inside the exponential, there is potential energy divided by thermal energy, which is the kinetic energy available for the free carriers, right? So some elementary statistical mechanic books or thermodynamics books can be referred to if you do not know the basis of this formula. So here V is the potential of the bulk with respect to reference electrode in the solution. That is, again, you take a voltmeter has two leads. One of the lead goes into the reference electrode, which is stuck inside the solution. The other lead goes into the electrolyte, wherein this potential is measured, right? So this is the potential measured with respect to reference electrode. So these kinds of measurements we have done, we have analyzed in previous lectures. So again, the basis of this was dealt with in this lecture, especially the part of this lecture wherein we looked at the effect of temperature, right? So we have considered concentration of the ions at infinity where the potential was 0. What is the concentration of the ions in a region where there is potential phi? And we have given the basis for this equation, which is like this equation, right? All these things have to do with Boltzmann distribution. There's a potential energy, kinetic energy term in the denominator. So please refer to this part of this lecture to get a clarity of on the basis for that equation. Let's move on. So we have this formula. How are we going to use this formula? We have also looked at all these features with respect to a semiconductor, N-type semiconductor, electrolyte interface. We have done all these things in previous lectures. So specifically, we are going to put all these things together and get to this formula. So what is this? This is the concentration of electrons at the surface. Okay, so at the surface of a semiconductor electrolyte interface, this is the concentration of electrons in the bulk. All these quantities have been clarified in the previous lectures. So we now have a formulation to obtain this quantity Ns. Why is this important? So let us spend some time understanding what we have here, what we have schematically represented here. So we have electrons that are present in the semiconductor. We have an oxidized species in the electrolyte. This oxidized species can accept an electron and can get reduced. So R refers to the reduced species that is present in the electrolyte. V refers to a vacant electronic energy level in the semiconductor. So this has been created because of a removal of the electron from, let's say, conduction band of a N-type semiconductor. So this process, that is electron combining with an oxidized species, is the cathodic process, gives rise to V plus a reduced process. And there can be reverse of this process, right? So wherein the reduced species gives up an electron to the vacant electronic energy level and generates O, an oxidized species in the electrolyte. So that is an anodic process. So you can have a dynamic equilibrium wherein the rates of the cathodic process is the same as the rate of the anodic process. That is indicated by this symbol here. So one way to accelerate the anodic and cathodic process is by applying bias. So that's the way we polarize an electrode and increase the rate of one of the rate processes, right? So this we have already done in the context of, let's say, a metal electrolyte interface. Here we have a semiconductor electrolyte interface. The quintessential feature of a semiconductor electrolyte feature interface is the band bending, right? This is the distinct characteristic of a semiconductor electrolyte interface. There is band bending, right? So let's understand what this band bending does when you have an electron that wants to get transferred to the electrolyte. This band bending provides an activation barrier, right? So if the electron's energy increases, therefore, this is like an activation barrier to get to the electrolyte. So if you apply a bias such that the effective positive charge in this region is increased, then the band bending increases as compared to this level. And by application of a bias, you can increase the activation barrier for charge transfer to the electrolyte. So in a way, if you're considering the cathodic process where there is the electron has to get transferred across this interface to the electrolyte, by applying a potential wherein this band bending is increased, that is, this is made more positive, then the rate of cathodic process is decreased. Okay, so this fits well with your idea of electron transfer across an electrode electrolyte interface. Supposing you consider the other scenario wherein the application of bias is such that effectively this region has become negative, therefore the band bending is in the opposite direction. In this case, the activation barrier for the transfer of electrons from the semiconductor to the electrolyte does not exist. Therefore, the cathodic process can be enhanced. So by application of bias, you can increase or decrease the rate of cathodic process. In this case, the cathodic process's rate is increased. In this case, the cathodic process's rate is decreased. Again, similar argument can be made for anodic processes also. So in the semiconductor literature, this scenario is called reverse bias. So in a reverse bias condition, the width of the depletion region is increased. In this case, this is called the forward bias region, where the width of the depletion region is decreased, right? So let's move on and let's understand how to derive a kinetic expression for current. So we have cathodic and anodic processes here. So the forward rate can be expressed as the rate constant of a cathodic process times the concentration of electrons at the surface times the concentration of oxidized species present in the electrolyte. The reverse rate can be represented in this. This requires some clarification. So, of course, the reverse rate is dependent upon the concentration of reduced species. That is obvious. That is present here. Why is that we have not mentioned this contribution? That is the number of vacant energy levels. So if you think through this, the vacant energy levels are present in the entire conduction band. So this is almost infinite. That is, large number of vacant energy levels are present in the entire conduction band. So by change in occupancy of conduction band, the number of levels is not significantly changed. Therefore, this can be more or less taken as a constant and incorporated into this rate constant Ka. Therefore, we neglect the change in variation of V because there is more or less a constant independent of voltage. And so the reverse rate is represented by a constant times concentration of R, right? So what is important to notice is this quantity is critically dependent on potential, but the reverse rate is more or less independent of potential. So it is possible to increase the forward rate, that is the cathodic processes, by applying potential, whereas the anodic processes are more or less independent of potential. So if you polarize a semiconductor electrolyte interface by applying bias and get the current response, the response is more or less like this. What is plotted here is a normalized current, I divided by some current. ICB refers to conduction band. We'll see what is the meaning of this. And along the x-axis, we have a dimensionless O potential. That is, we are applying a bias. Therefore, that is indicated along the x-axis. So in one side, that is in the positive side, the current is more or less independent. That is, the anodic processes are more or less independent of the potential which is applied. So that is what is seen here. And the cathodic processes, that is, see, you have a negative potential here. So the cathodic processes are significantly affected by the potential. The current response in this semiconductor electrolyte interface is very critically dependent on the potential applied, and the cathodic current, that is indicated by the forward rate, is exponentially dependent on the potential that is being applied. So this is called forward bias cathodic current. This is the reverse bias current that is more or less constant with potential. So this entire region can be represented using this formula. So you have this quantity, that is this quantity, this so-called the exchange current density. This is the O potential that is supplied, that can be cathodic or anodic in nature. So at some point, the current is zero, right? So here you have a zero current at O potential is zero. So when this zero, this becomes 1, the overall current becomes 0. That is indicative here. So when eta is positive, this is going to be a large number. So effectively, this quantity will become 0. So this is independent of O potential and is more or less same when you vary the O potential in the anodic region. Okay. And that is more or less some constant quantity. Okay, so so this normalization is ICB. Okay, so it's not exactly ICB naught. Okay, so this variation is shown here, and when you have a negative O potential, that is the cathodic O potential, this quantity negative times this -1, this will become a positive quantity. So that will have an exponential variation in after some O potential in the cathodic region. This can be neglected, and this variation can also be represented. So both the variation in the anodic O potential and the variation in the cathodic O potential can be represented using this formula, right? So this is just Farad. That is, you multiply charge times Avogadro number. So Kb, the Boltzmann constant, becomes R. This becomes F. So all these things are put together. This is just the same thing presented, except you show the variation in band bending. So this region is the forward bias region, where there is an exponential increase in the cathodic current when the cathodic O potential increases. Here, this is the reverse bias region, wherein there is a significant activation barrier for the transfer of electrons from the semiconductor to the electrolyte interface. This can be mathematically represented. That is, the current variation with O potential can be represented mathematically here. So here we have described the charge transfer for an N-type semiconductor interfaced with an electrolyte. A similar analysis can be made for a P-type semiconductor. So in a P-type semiconductor, the current exponentially increases in the anodic O potential region, whereas in the cathodic O potential region, the current normalized to IVB. VB refers to the valence band. Here, CB refers to the conduction band. So the majority carriers is different in an N-type semiconductor. The majority carrier here is the electron. Majority carrier here is the hole. So we would be thinking more about the hole current. So for an N-type semiconductor, again, the potential dependent can, the current can also be mathematically represented in a different manner. Corrected the typo. This is the correct expression. So both an N-type semiconductor interface with an electrolyte and a P-type semiconductor electrode interface with an electrolyte can be represented via this polarization curve. So current response when you change the O potential. So in the next lecture, we will look at light absorption in a photoelectrochemical system. We thank you.